In this video, we're going to be looking at geologic structures, and this is really a look into how the crust of the Earth is deformed. So let's make sure we know what this means. Deformation is the process by which rocks bend, break, or flow in response to stress. And so during this series of lectures, we're going to be looking at that bending and breaking of the rocks. Now, geologic structures form because of deformation. These are your results of deformation. And there's a list here of all of your geologic structures. These include anticlines, plunging anticlines, synclines, plunging synclines, monoclines, domes, basins, normal faults, detachment faults, reverse faults, thrust faults, left lateral strike slip faults, right lateral strike slip faults, and oblique faults. Now, these are all the ones you're going to need to be able to identify for class. And just to make matters a little more complicated, for each one of those, I need you to know how to recognize the map view, the cross section, the ages of the rocks within the structures, the strike and dip symbols, the stress type that forms it, and the plate tectonic boundary where it occurs. That's a lot of information, but it's really not as bad as it sounds because I'm going to show you some tricks to kind of help you keep them all straight as we go. You should be just fine. So let's review our types of plate boundaries really quick since that's going to be one of the things on here. So remember, we have convergent plate boundaries. That's when two plates come together. We have divergent plate boundaries. That's where the two plates move away from each other. And the transform plate boundary, where two plates slide past one another. Now this is going to be really important because we're about to start talking about stress. So stress is a force applied to an object. So in this case, in the little GIF here, you could see that the finger is pushing on the block, and that's the force. But notice the block is actually moving because of that. That's called strain. So strain is the result of stress. So we're going to look at different types of stress that we can apply to a series of rocks. So our first type is compressional stress. In compression, the rocks get squeezed, and you can see in the blocks here, it's narrower, but it ends up getting much taller. We have tension. And I always like to think of tension rods that you use to hang up your shower curtain, right? You pull them apart as far as you can, and it hits the side of your shower, and that's how it stays up. So tension is going to stretch rocks. It makes them thinner but wider, which is pretty much exactly the opposite of what compression does. Our last one is going to be shear stress. Shear stress tends to smear the rocks. And I always like to think of kitchen shears. What's a kitchen shears? It's just a pair of scissors. And if you think about the blades of the scissors, the reason why they cut is because they slide past one another. And this is what's happening here and with our direction of force that's applied here. So in this case, they get longer, but they basically stay the same width overall. Now, the type of deformation. So rocks are going to react to stress. Now there's three ways rocks can react. In one, we have elastic deformation. So if you think of like elastic waistbands on your pants, right? The rocks are going to bend but return to the original position when stress is released. So here's you a GIF of some materials deforming elastically. Notice it pops right back into that same position and that same shape every single time when one of the little goats hops off. In plastic deformation, the rocks bend, but they stay bent when stress is released. And this guy apparently holds the world record for bending metal rods. There's a record for everything. But notice he bends it. Oop, there it goes. And it stays bent. And finally, we have brittle deformation. This is the case where rocks break. And there's somebody breaking some materials there. Notice it's going to stay broken in this case. Now, the type of deformation, whether a rock undergoes elastic, plastic, or brittle deformation, is going to depend on a few things. For one, the temperature of the rock. If it's cold, it's going to more likely undergo brittle deformation than if it's warmer, it may bend a little bit. It's going to depend on the rock type. There's certain rocks like shales, like claystones, like mudstones that like to bend pretty easily. And it's going to depend on the rate of stress. The only reason why this guy can break all of those bricks on the bottom there is because he does it quickly. If he were just to stand on it and kind of push down a few times, they're not going to break. But if you apply the stress really quickly, it is able to break. Now, the ones we're going to be looking at are these last two, the plastic and the brittle deformation for this. We're going to look at when rocks bend, and we're going to look at when rocks break. Elastic deformation we're going to save for just a little bit, but we will come back to it because that is why we have earthquakes, is because of elastic deformation. So I want to make sure and look at a couple of terms and things about how we look at rocks before we continue, because this is going to be really important for understanding the three-dimensionalness of our geologic structures. All right, so there's two ways we can actually view rocks in geology, or at least the how we report what they look like. And the first thing we look at is the map view. So this is if you're above in the sky looking down on the rocks. And it's called map view because this is what maps look like. For instance, here's a geologic map, and you can see there's gabbros and troctolites and leucogabbros and volcanics and a granophyre, hornfels. You've probably heard of hornfels and quartz diorite, right? Those are kind of some weird materials there for you. Now, you can see through here it sort of makes kind of U-shaped. What I would assume is that it probably was like a bullseye at one point, and some of these have messed with it since then. But what if we were to take a slice of it, just like we do a cake, right? So this is like looking at the top of the cake. It says happy birthday. But what if we want to see those layers of the cake? How many layers are in there? In that case, we're going to use a cross section. You take a slice of that rock and then look at it from the side. And these are cross sections of that same map. Now it's cross sections from different angles. So for instance, this is going to be starting out like on the south part and going north because you can see kind of these weird diorites and stuff up here. And this is going to be cutting in a different way. So if we look back up here to map view, so the top one is cutting it from the bottom going up, kind of to the northeast. And that bottom one was actually cutting it straight across. And so you can see what rocks you see really, it looks a whole lot different based on where you cut it. And that's going to be important for cross sections because for our geologic structures, the cross sections look really different depending on which way you slice it. All right, now what you notice probably in those is those rocks weren't nice and flat, and rocks aren't often nice and flat, but we need a way to describe what that looks like. All right, so for instance, let's think about this set of rocks right here. So if we look here, we can see these rocks obviously aren't horizontal. Now, the principle of original horizontality tells us they were at one point, but they've since been tilted over. And we can get a kind of an idea of how just tilted it is because that top of the water is always going to be flat, and that's important here. All right, so we can be like, well, it's tilted over to the side. Well, it's tilted to the right. It's pretty steep. It's kind of going towards me just a little bit. So it's kind of hard just to describe it. But what I'm going to tell you is there is one little bitty, itty tiny picture we can draw on a map that tells you exactly what this looks like. So that is called strike and dip. So the strike is the angle between an imaginary horizontal line on a plane and the direction of true north. So let's imagine, so this right here, this edge of my little block, that's actually the top of those rock layers. Works pretty nicely, right? Now, where that ocean touches the top of the rock layers, you can see that right there, thanks to a little bit of, like right there, that's a perfectly flat area. So what we're going to do is we're going to figure out what direction that's pointing. You know, if we assume north is looking forward, that's kind of pointing off to the northeast, right? So that's the strike of a rock. And then the dip. So we imagine water running down that same top of the surface, or at least the top of your layers. Whichever direction the water is going to run, that's your dip. So the dip is the angle between a horizontal plane and an imaginary line parallel to the steepest slope on the structure. So we're looking at the steepest slope, right? So let's go back and look at this rock again. Oh, sorry. Here is another example of it. So here's rocks. They're dipping to the side. So you can see there's those layers dipping. We found the top of the layer. We're going to figure out which direction that line of strike is at. And that is your strike. This is a strike and dip symbol right here, so that's showing you where the strike is. And the water runs down this way. That's the direction of dip. That's why this little tooth points that way. Now, we can measure strike and dip using a pretty easy tool. It's this guy right up here. This is called a Brunton compass. So the Brunton compass is obviously a compass, so that measures the direction of strike pretty easily, but it's specially modified to be able to also measure the dip, and you're going to use these in lab. So what we're going to do is we're going to go back to this picture, and let's look at what the strike and dip for this is. And for this, we're going to look at it at a couple different views. This is obviously a cross section, right? Because we're looking at it from the side. So what we can do is we can actually look at that angle of dip. So your angle is right about there, right? And I tried to line this up with the top of a layer. The top of the layer is pretty important. So we're going to look at this angle right here, and to do that, let's pull in as a protractor. I'm going to get rid of the picture so you actually see what's going on. And what we find is that is right about 47 degrees-ish. All right, that'll work for right now. All right, so it's dipping at 47 degrees. Now, what direction is it dipping? Because we need a direction. Well, if you remember, it was at least dipping towards the ocean, right? So this is how you'd actually measure the dip versus getting a protractor out. The Brunton compass has a little arm. It can't really see it inside here, but there's a little pendulum in there that helps you measure the dip. So that's what she's measuring right there, is the dip of a rock. This is what that area looks like from above. I actually pulled this off of Google Earth. And if we look, we can actually see those rocks all tilted over there. We're going to zoom in. It's a little messy, but this is as good as it gets right now on Google Earth. So this kind of lines up with those layers, right? So that's your strike. Because if you actually went out there, that would be the top of one of those layers. Now, if we were to hold our compass out, then we'll look at where the arrow points. This is what it's going to look like. So in this case, we always measure strike from north. So this is north, but if we go over like 43 degrees, all right? So it's 43 degrees from north, but it's 43 degrees towards the east. So in this case, we say it's north, because we always start with north, 43 east. So that's going to be your direction of strike. Now our dip, if you remember, our dip was towards the water. So in this case, they're all going to dip to the northwest. And that makes sense, right? Because if it strikes northeast, it has to dip northwest, because strike and dip are always perpendicular to each other. And here is somebody measuring the strike of a rock. Basically, you hold your Brunton compass nice and horizontal, and then you put it up against the side of the rock face and measure that direction. It's actually pretty easy. So let's draw a strike and dip symbol then. This is what's going to go on a geologic map. I'm going to put this same kind of compass back up just to help us measure it out. You can need a compass, protractor, whatever you got to measure it. All right, so if you remember that strike was north 43 east. So I'm going to draw a line. And if we look, if we send this one out, it goes to 43 east, which is good. Once you have your strike line drawn, you can put in your dip. Now, strike and dip are always perpendicular to each other. And in this case, you don't actually have to measure the direction of dip because you already measured strike. So all you have to do is draw a line perpendicular. And if you remember, we looked and it was dipping towards the northwest. So we're going to draw a little line pointing northwest. That's the easy part here. Now, it was dipping at about 47 degrees. So what we're going to do is right next to that, we're going to put a little 47 there. Take away our protractor. There is the strike and dip symbol that would go on the map. And this right here describes all of what those rocks were doing. So it's a beautiful little symbol. Now, sometimes rocks are dipping much more steeply. In this case, these rocks are actually almost vertical. And if we look at the Grand Canyon, here's an example. The rocks above are nice and horizontal. The rocks below are tilted at an angle. If you remember, this is an angular unconformity. Now on a map, we've already looked at one example of that. So for here, you can see you've got layers that are inclined or tilted over. Strata just means layers. And since it's tilting to the right, we could say, I always imagine which way you would slide down. In this case, you'd slide down to the right, so it's going to be, this dip is pointing to the right. So this is the cross section. This is the geologic map. Now, if those layers are nice and horizontal, we put a little crosshatch there just to tell you, yeah, we checked that, but it's horizontal. If the rocks are vertical, like this, it makes a line across the map, and you make this little cross. So that's what those look like on a geologic map. So let's practice just a little bit. Here are some rocks from Nepal that are tilted. So which one of these two sets of strike and dip symbols accurately describe this cross section? Hopefully you said that one because they're pointing to the left, right? And you could tilt to the left, you'd slide down that way. What about this? This is from Costa Rica. Which one of these is correct? Well, that's just the opposite. You see the one on the top is tilted to the right. How about this one? Oh, it's a little weirder now, isn't it? So in this case, the rocks on the left side are tilted to the right, and on the right side, they're tilted to the left. It's actually this guy. This one is going to do it. This is a special kind. We're going to get to this fold right here. This is going to be important. You'll know exactly what this is here pretty soon. What about this? This is from, I believe, northern Arizona or Utah. Oh, did you notice none of those is actually right? This is totally a trick question. In this case, these rocks are tilted to the left, so this symbol here is correct. But these rocks on the right side of the screen, those are horizontal. Ah, remember our little horizontal. That's what this one looks like. This is another one of those folds you're going to know how to identify here pretty soon. All right, in the next video, we're going to look at those folds and then faults, and we're going to see how to identify the actual different types of structure.